Hello, hello. Okay. Okay, is this working? Yes, please. Well, okay, I'll wait.
Okay, so let's start as soon as we are ready.
Enjoy the papers.
Everybody ready?
Okay, I will. So, hello everyone. My name is Cristóbal. I'm a first-year postdoc at Las Campanas Observatories down in Chile. And today I want to talk to you about some work that we're close to publishing, in which I will discuss metallicities of a redshift 7 protocluster. This work is in close collaboration with Crystal Martin, Wei-Da Hu, and Aveda Yang, and the rest of the Lager/Sider collaboration. So I plan to skip this because I thought we would have an afternoon of reionization. It was not the case, so I will briefly cover reionization. Basically, we know that the universe, the IgM, was neutral here, and now it's ionized. Something happened. What happened? Reionization. So that's the period when the IgM went from almost fully neutral, to almost fully and also a phase transition of most of the baryons in the universe. So it's and also, as Andreas said, and I like the way he put it, it's a boundary condition for galaxy evolution. So we should pay attention to reionization. This is just to show you how it happened. These are different models. This is just to show you the shape of the curve. So basically, we had this is the neutral fraction. So at some point, it was fully neutral, and it quickly evolved to a fully ionized IgM. So we want to learn more about reionization, how it happened, which sources were responsible for it, and that's why we began a project called the Lager survey. So Lager, Lyman alpha galaxies during the epoch of reionization, is a Chile, China, and USA collaborations. We built a custom-made narrowband filter, you can see here. So this filter is matched to the Lyman alpha wavelength at a redshift of 6.9. We aim for that redshift because, well, it wasn't fully explored, and also there was some good atmospheric transmission. It wasn't, full of skylines in that range. Otherwise, it would be hard to observe. The filter is mounted on the DECAM instrument at the 4-meter telescope at Tololo. And the combination of this very sensitive instrument, the large field of view make Lager a very efficient survey. So far, we have found around 200 to 300 Lyman alpha emitter candidates and confirmed around 30 of them. So we are very happy with Lager so far. Something very interesting that we found is this protocluster. So this was reported by Wei-Da Hu in 2019. First, just as overdensity of photometric sources from the narrowband survey, but then we got spectra, a lot of spectra, and we confirmed that 16 sources, so the solid sources, so the one filled with red, yes, the 16, were actually Lyman alpha emitters. So with that, we could confirm that we were looking at a protocluster. So protoclusters during this epoch are very interesting because there's a lot of star formation rate going there. Some estimates show that 50% of the star formation rate density happens inside protoclusters. So, and as we believe that star formation is the main source of ionizing photons for reionization, protoclusters become a very interesting system to study how reionization is taking place. So we wanted to learn more about these sources. Before I jump to protoclusters, I want to briefly mention optical red frame spectroscopy. You will know why. But I want to tell you that we can learn a lot of things from optical red frame spectra. In particular, we have the hydrogen recombination line and the oxygen recombination line, and we can learn important parameters such as the gas phase metallicity, the electron temperature, and density. And in this figure, I'm just showing you how one can use some line ratios. In particular, I want you to pay attention to this. So this is the line ratio between oxygen 3 and also oxygen 3, but a different transition. When you have different species of the same transition, you can estimate the temperature. And if you know the temperature and a density, you can get a metallicity. This is what is called the direct method. So if you find one of these important lines, some of these lines, you can then directly constrain the metallicity. And that's what we wanted to do. We got a JWST proposal accepted. I'm going too fast, sorry. To observe some of these sources with the MSA. So we aim to, the wavelength ratio of 3 to 5 microns allowed us to cover all of the optical lines between O2 and H alpha. So this was a bunch of information that we could get. In this work, I'm showing you the spectroscopy of 6 of the sources. So we got the spectroscopy for 8, but I'm showing you 6 here because the other ones were missing some key lines to do the strong method diagnostics. The full sample will be presented in a paper by Crystal Martin, which has already been submitted. For now, I want you to pay attention here. So, these are the 6 sources. So 1, 2. So each source has 2 panels, 3, 4, 5, 6. Because on the right panel, I'm showing you the oxygen 3 5008 or 4950 line. And on the left-hand side, I'm showing you H gamma, and this is the aurora line, oxygen 34363. So this is the tricky line that we want to measure metallicities directly. Something interesting that I also want you to see is that these have a clumpy morphology that will become more or less relevant. We had our line detections in all of these sources, and with that, we can go ahead and measure the metallicities. Let me briefly mention, well, not briefly, let me talk to you about some of the methodology that became relevant. So, as I'm telling you, these are clumpy. So we are only interested in one clamp because we can really, it becomes tricky if we try to compare or to measure the things for both systems, because sometimes lines are only present in one clamp and not the other. So what we did is to measure the morphology of this clamp, feed it with 2 Gaussians, and then we do a weighted extraction using only the Gaussian profile that we're interested in. So for example, in here we feed these 2 Gaussians, but we only want this clamp over here and do a weighted extraction using this profile. We are interested in line ratios, so this shouldn't be a problem. Because the flux that we get with just raw extraction will be different as the flux that we get from a weighted extraction. But again, these are line ratios, so that will cancel out. Another important thing is the aperture losses. So yeah, of course, we don't fully get the source with the MSA, especially because the MSA, as you know, you can't really create a custom slit. You just open and close the shuttles. So we run the MSA fit program. So MSA fit, what it does is you give it a morphology, a position in the MSA, and it propagates the light, basically the full light path, optical path that is traversing, and then it gives you how many of the photons that you had originally ended up in your image. As you can see, these are rather smooth. Oh, sorry, first, forgot to tell you that we measured the morphology using Galfit on the JWST images. Yeah, so these are rather smooth. There's not much difference between both ends. Right? In some extreme cases, you might go from a 50% transmission to a 65%. So that could lead to some problems when we're taking the ratios. But again, this is within the errors. But we still wanted to do this correction, particularly for future proofing. Sometimes we might want to compare line ratios taken in different configurations of the MSA. In that case, you do need to apply this and be very careful. But in the end, it didn't matter too much to us.